The invention of the Kearney-Fushida drive in the early 22nd century, so named for the two scientists who first conjectured that such a device was possible, revolutionized space travel like nothing else. Until that point, journeying to even the closest star using conventional fusion rockets would have taken a lifetime, a voyage you would never return from. These days, travel between worlds is entirely routine and might only take a couple weeks, with a KF drive allowing a vessel to jump from one system to another almost instantaneously. Yet despite how commonplace it is in our modern society, few people have a grasp on how such a device functions, nor the rules and limitations on its operation, save for the crews themselves who have an intimate understanding of this dark art. This video isn't intended to be a technical breakdown of the complex physics at play whenever a Kearney-Fushida drive is activated, but rather serves to explain in layman's terms what it can and can't do. In essence, it allows for teleportation between two distant points via movement through hyperspace. A jump drive, as KF devices are colloquially known, consists of four main components: the field initiator, drive core, cooling jacket, and controller. The initiator creates the hyperspace field through which it will pass to reach its destination. The core itself, constructed from a complex titanium-germanium alloy, acts as a large capacitor. It both provides the necessary energy for activation and focuses the field's dimensions so that it surrounds the vessel onto which it is mounted. Without the core, the initiator would only transport itself, tearing free from whatever structure it was bolted to. The liquid helium cooling tank encapsulates both of those parts and ensures that the jump drive remains at the correct operating temperature. The controller regulates every other component's activity. Kearney-Fushida drives require an enormous amount of energy to operate. It was for that reason that the initial research back in the 21st century was never followed up on, as no fusion power plant at the time could possibly have generated the required output. Charging the device takes approximately a full week of continuous burn, an extremely fuel-intensive process. But these days, the use of reactors to perform this function is reserved as a backup. Since the 23rd century, enormous solar sails over a kilometer in diameter but barely a millimeter in thickness have been the standard, providing a functionally unlimited source of power. Care must be taken to match a specific sun's output by limiting the extent to which these solar panels deploy so as to not overload the delicate drive cores. While it is possible to quick charge a jump drive, doing so carries with it a not insignificant risk of damage. Connecting to a recharge station can reliably bring that time down to 5 days, but less than that is not advised. Theoretically, a full charge could be achieved within a single day, but in all probability, those 24 hours will likely be your last. Activating the device takes approximately 10 minutes, not including the sometimes lengthier process of calculating a target destination first. Once it is committed, the operation cannot be aborted without a loss of charge, or even damage if cancelled in its final seconds. A last-minute change of destination is the best the crew can manage at this stage, a process that carries its own inherent risks. At the moment of departure, nearby objects will be subjected to strong gravitational forces. A person clinging to the exterior hull might be unharmed, but another vessel alongside will likely be torn asunder by the tidal stresses. If another drive core is within 25 kilometers, the interplay between these two devices can be disastrous, as each attempts to shape the hyperspatial field around themselves, resulting in the loss of both vessels. For this reason, jumping a replacement core through space is functionally impossible. The primitive Kearney-Fushida drives of the 22nd century had a maximum range of just 15 light-years, but this gradually ramped up over the decades. By the 23rd century, it had increased to a more practical 30 light-years. Later experiments have failed to extend this any further, though there are occasional reports of desperate ship captains managing to eke out another 5% to complete an emergency jump just over that figure. Not all jumps are made between two stars. Occasionally, vessels will move within a system via hyperspace, either swapping ends or moving to another location after making an observation. Any activation will deplete a drive core's energy completely, irrespective of distance covered. But some brave captains have chanced intrasystem jumps a few percentage shy of the recommended full charge. Needless to say that such behavior is not covered in the owner's manual. Theoretically, there is no minimum range for a jump, but through a quirk of physics, the drive core can create its own interference if it attempts to move within 25 kilometers of itself. One of the more peculiar aspects of interstellar travel is the way that it affects the perception of time. From the perspective of everyone on board, the passage of time comes to a halt during the jump itself. Anyone who has experienced KF travel themselves can attest to the fact that conversations can flow uninterrupted across vast distances. The most a person might experience are visual distortions as points of light stretch, expand, and contract. Further complicating the issue is the fact that the ship's internal chronometer does not record any interruption, but the common belief in instantaneous teleportation is actually fallacious. Moving through hyperspace does take time. The actual duration for a max distance jump typically ranges from 15 seconds to just over 2 minutes depending on the size of the vessel, or more accurately the size of its hyperspace drive and extension booms. Some of the largest behemoths from history pushed that out to over 6 minutes to cross 30 light years. Shorter distances require less time on a fairly linear scale. Once a vessel is underway, various phenomena can be observed at the destination point as space begins to warp. First, an infrared signature heralds the arrival of an incoming jump. Then, in the final fractions of a second before it materializes, a burst of energy annihilates any stray atoms occupying that space, giving off a pulse of electromagnetic radiation known as an emergence wave. Electrostatic repulsion pushes any remaining particles away. An instant later, the Kearney-Fushida-equipped craft completes its jump, having most likely travelled multiple light years and simultaneously altered its velocity to match its new orbit. So far, we've covered everything that a jump drive can do, but one of the main constraints on what it can't do relates to the precise locations at which it disappears and re-emerges, what are known as jump points. As previously mentioned, they must be within 30 light years of each other, but there are a host of other limitations on that, though even those have some exceptions. The most significant obstacle a ship's crew are required to work around is that the stars themselves interfere with KF travel within a certain distance. A given sun's gravity well is typically understood to be the chief culprit, but other aspects play their own part in disrupting normal function. As such, at the heart of every system is a sphere within which a vessel cannot conventionally depart from or arrive at by means of jump drive. Only beyond that region of space are the tidal forces minor enough that they do not prohibit its use. This cutoff is known as a star's proximity limit, which varies in radius depending on its stellar mass, luminosity, and temperature. The most massive astronomical objects require the greatest distance. It is because of this figurative no-fly zone that people cannot simply teleport from the surface of one planet to another. Travelling between worlds still takes weeks because the first and last stage of the journey is the transit time up from the surface out to the very edges of the system, and vice versa at the other end. A common misconception is that jump drives can only function in areas of zero gravity, but this is not the case. In our home system of Sol, the proximity limit lies just beyond Saturn, well inside the orbit of the outermost planets. It's worth highlighting now that every stellar object has its own independent proximity limit, but they typically fall within a star's larger area. Jumping to Neptune, for example, still requires a clearance of over 1.5 million kilometers, though that is practically right on top of it in terms of astronomical units. In theory, a KF drive-equipped vessel can come and go at any arbitrary point out with a star's gravity well, But in practice, the vast majority of jump travel passes through one of two locations along a star's rotational axis at a distance appropriate to its stellar properties. We call these jump points zenith and nadir for a system's north and south pole respectively. Their use is so ubiquitous, anything else is referred to as a non-standard jump point. These could be further out, theoretically even in the empty space between stars, or they could be right at the limit, but offset from the poles, in which case they are known as proximity points. There are several reasons why the zenith and nadir are most commonly used. The first is a simple safety precaution. The more ships that pass through a single location, the greater the odds that another crew will be on hand to lend assistance if a vessel flounders. Likewise, only a limited number of space stations are constructed each year, and so the presence of any one of these is going to focus traffic into the area around it, as crews seek to make use of any permanent facilities at that location, whether that be recharging, supplies, or recreation. Space stations are, for the same reason, most often placed where space is busiest to be of the most use. While that answers why jump travel is concentrated in fewer locations, why zenith and nadir specifically? As you approach the orbital plane, the gravitational pull of the planets can extend the sphere of influence outwards. In reality then, the proximity limit is slightly ovoid in shape. It can still be beneficial to arrive at a non-standard jump point if you're heading for one of the outer worlds, but it might actually extend the distance to the core planets, which are invariably the ones inhabited by other people, reaching which is your most likely end goal. A position above the poles standardizes any intra-system travel time regardless of a planet's position along its orbit. If a navigational computer lacks information on the real-time location of a target world relative to its star, choosing another proximity point could result in a longer journey if it lies beyond the Sun at the moment of orbital intercept. The zenith and nadir are also the easiest jump points for a ship's navigator to calculate, taking only a handful of minutes to plot compared to hours for non-standard ones. Uncharted systems can be arrived at safely based on observations made literally quadrillions of kilometers away. Trying to determine how the orbital plane of unknown planets might impact the proximity limit away from the poles is a needless complication. Even in the case of computer malfunction, a trained navigator can do the necessary calculations by hand, applying only a slight safety margin to bring them in a little further out than usual. On the face of things, an abundance of spacecraft all passing through a relatively small area of space could present its own dangers in busier systems. With no way of checking in advance whether something already occupies your targeted point of arrival, and with that object only having seconds to clear the area upon detecting an IR signature, it's feasible that you could materialize inside another vessel. Thankfully, such incidents are exceptionally rare. To minimize the chances of malfunction leading to disaster, a standard practice has developed to aid ships traveling by Kearney-Fushida technology. Upon arriving at a system, ships allow themselves to freefall a short distance towards the Sun before arresting their momentum, coming to a standstill just inside the proximity limit and deploying their solar sails safely out of harm's way. Likewise, permanent facilities also hold station just inside of the zenith or nadir. Therefore, the only objects an incoming ship needs to avoid are outgoing vessels. Contrary to popular belief, a Kearney-Fushida drive does not need to be stationary relative to the nearest star to use. With a small additional calculation, they can just as easily jump while under thrust heading outwards, with sufficient velocity to clear any incoming craft detected in their path. Only in truly unfortunate circumstances has this been insufficient to avoid disaster at the jump point. But all of these precautions belie the fact that jump points, even those as specific as zenith and nadir, are vast, thousands of kilometers across. Most civilian crews don't even bother to do their jump calculations with a precision that would guarantee a drift of under 5 kilometers, because the target they're aiming for is bigger than a planet. The odds of two ships intersecting is extremely small. One of the largest fleet movements in history had almost 500 ships arriving at the zenith and just as many at the nadir in groups of 20 on 5-minute intervals, with only a single unfortunate collision due to an engine malfunction. While the zenith and nadir are the standard jump points, ship captains do occasionally make use of other locations. The most common of these are Lagrange points. Any set of 2 astronomical objects share 5 such locations. The first lies between them at the point where their gravitational pulls equalize. In the case of a sun and planet, this naturally is much closer to the latter. The second lies beyond the outer of the 2 objects, where a higher speed would typically cause an elliptical orbit, but instead the gravity of both pulling together keeps it locked in a circular one. The third lies opposite the object of lower mass. The fourth and fifth lie along the orbital path of the smaller object, approximately a sixth of an orbital period ahead or behind respectively. These zones of equilibrium allow a Kearney-Fuchida drive to materialize well inside of a star's proximity limit. How often these are used depends on several factors. Before any navigator would consider aiming for such a target, they would need to know the real-time location of a system's planets, instantly ruling it out as a possibility for uncharted systems. Crews who ply a small sector of space might have up-to-date charts for their regular stops, but more far-ranging transports are only going to have that information on hand for the most heavily populated systems. Similarly, the worlds that see the greatest volume of interstellar trade often have the most thoroughly mapped out Lagrange points, allowing for reliable calculations. Only the most foolhardy would risk a jump to a system they are unfamiliar with. The flip side of this coin is that the planets with the largest populations often have the tightest defenses. Lagrange points are frequently reserved exclusively for military or government purposes. Woe betide anyone who arrives unannounced at one of these locales. There are other reasons to pass over these spots. The L1 and L2 are extremely small targets to aim for. The slightest miscalculation can result in you materializing deep inside a gravity well, with predictably disastrous consequences. Additionally, both of these become unusable with the presence of a large moon or moons, further complicating the tidal forces. L3 are avoided for their lack of practicality. Put simply, there is a sun between you and your destination. Some have used this as a means to mask their entry into a system, since it obscures their IR signature and emergence wave, but any moderately defended world will have observation satellites in place to report such activity. There is a sweet spot that exists at the L4 and L5 points, and it's these locations that see the majority of use as non-standard jump points. The table in the gravity well they sit on is comparatively broad, giving a more generous margin for error in drift. The distance to a planet is much shorter, but not so short that their use is heavily policed. Here, the risk lies in Trojans, asteroids that have been pulled into a stable orbit that already inhabit that space. Similar clouds exist at the L3 point as well. For this reason, consulting accurate star charts is a necessity before any attempt to navigate here, as a JumpDrive's electromagnetic pulse can annihilate at most just 1 kilogram of material lying within a jump point. Though a vessel might only suffer minor breaches, humans tend to be more susceptible to damage caused by rocks materializing within themselves. There is another kind of in-system non-standard jump point a vessel can make use of, a transitory position that might only exist for a fleeting moment. It relies on the interplay between several stellar bodies, perhaps even multiple suns in the case of a binary system, as their competing gravitational pulls briefly cancel each other out. These locations are most often given the inauspicious title of pirate points, so named for the type of desperate individual that frequents them, but officially they are called transient points. The risks here are the most extreme. You are deep inside a star's gravity well with nothing to help anchor yourself in place, and the target you're aiming for is tiny. Some rare systems have transient points that appear regularly enough that their use has become slightly more common over time, after generations of risk-takers mapped them out. But few captains would take that chance. The classification of jump ship originates in the 25th century. Older Kearney Fushida drive-equipped vessels were typically hulking transports that carried their payload internally in cavernous cargo bays, relying on shuttles to take on or unload goods. The advent of the KF boom allowed for the attachment of smaller craft, dubbed dropships, to the exterior hull, safely enveloping them within a JumpDrive's area of effect through communication with the drive core. This led to a transition in design where JumpShips took on the appearance of narrow, needle-like craft with minimal interior space that served only to move dropships between systems, whereupon they would disengage from the docking collar and drop down to the surface. Technically, the term jumpship encompasses any vessel equipped with a KF drive, but there is another classification used in common parlance that applies to a specific subset of these. Primitive hyperdrives were largely superseded by the standard device in the 2200s, but a century further on, the development of the compact drive allowed for the construction of much heavier vessels. The cores themselves vary in size depending on a jumpship's overall tonnage, but they will always account for approximately 95% of that mass. Compact devices make up decidedly less, and this extra weight is most useful in the design of military vessels. With the cost being so much greater and the benefits of little use to civilian ships, any craft fitted with one of these advanced compact cores is a warship, even if a select few warship classes lend themselves more to observation than battle. The next revolution in jumpship design came in the 26th century. The invention of the lithium fusion battery allowed any ship equipped with one to store 2 full charges for its jump drive, functionally doubling its range. Over a distance of under 60 light years, this can cut a week of travel time, but the benefits become harder to quantify the longer a journey becomes. Drive core and battery need to be filled separately, requiring the typical 7 days each unless one risks a quick charge. This can be done simultaneously if you have the fuel to burn in your reactor, but modern jumpship designs don't even carry a single charge worth, so it's dependent on the attached dropships. A recharge station can use microwave beams to provide one charge while a vessel deploys its solar sail to capture the energy for another, but not every route will have those. Stations rely on their own sails for power and can store 8 charges at most, but there's no guarantee they'll be available upon arrival if it's a busy system, which is where such facilities often lie. At best then, lithium fusion batteries halve the time to cross space by eliminating a lengthy layover partway there, but in practice, their impact decreases over greater distances. As a final note, standard practice is to wait 1 day between activations regardless of available charge, except in the case of emergencies. Triggering a pre-calculated second jump immediately after the first risks causing damage to the KF drive, which when it comes to hyperdimensional travel is something best avoided, lest you suffer a dreaded misjump. A misjump is a fate feared by crew and passengers alike. Such a phenomenon can take many forms, from inconvenient to fatal. The point of arrival might be off by a few astronomical units, or, heaven forbid, several light years. In rare incidents, a jump ship has been flung across space far beyond the maximum safe range of their jump drive by an order of magnitude. Worse, there are times where only debris materializes at the other end, or nothing at all. Some speculate that there are a handful of unlucky ships trapped in hyperspace, but are otherwise unharmed, and will perhaps one day reappear at some point down the line. There are some whispered rumours of a vessel arriving at its destination years or even centuries after vanishing. It's also theorised that the opposite could transpire, something emerging from the future, though no examples of this have ever been recorded. In conclusion, the Kearney-Fushida drive arguably remains the single greatest scientific achievement mankind has ever made, even a millennium after its invention. While it pales in comparison to the technology depicted in some science fiction, its importance cannot be overstated. Without it, interstellar civilizations would be impossible, and with no means to transport people or goods between worlds, society as we know it would collapse. It is for this reason that JumpShips and their crews remain inviolate, even between bitter rivals. The destruction of even a single vessel is a greater loss for humanity overall than it is to any specific owner. In their lifetime, Thomas Kearney and Takeyoshi Fushida received nothing but scorn for daring to contradict physics as they were then understood. Looking back from the future, their position among the all-time greats of their field is undisputed. Well guys, I hope you've enjoyed this video looking at the intricacies of JumpDrives, JumpPoints and JumpShips. I know it's a little bit different from the mainline BattleTech history I've been covering on the channel, but it's an idea that I've been toying with for a little while now. It was really a couple of comments I received 1 or 2 months ago that expressed confusion about how interstellar travel worked in universe that gave me the impetus to sit down and write something. There are a lot of misconceptions about how jump travel works, both among the fans and occasionally the authors themselves, but it's actually something that was outlined from pretty early on in the IP's history. I think it was either 1986 or 87 where the sourcebook DropShips and JumpShips came out, and that really covers about 90% of it there. While this video included details from a number of different places, by far the main source for it was the Strategic Operations rulebook. It includes an enormous wealth of detail there. After reading it, I actually rewrote my entire script and doubled it in length. There was just so much information there I thought would be good to include in this video. If you enjoyed the video today, or if you found it in any way helpful, please give it a like. You can help the channel by leaving me a comment below. I try to respond to as many of you as I can. I know there'll be some questions about this one, so I'll try and cite my sources wherever I can. If you want to see more videos like this one, you can subscribe to the channel, and if you know anyone else who's having trouble understanding the specifics of jump travel, and you think this video might be helpful to them, please share it around. That really helps support me as well. Either way, thank you again for watching, and I'll see you soon on another video.